Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, guys. We start our lecture now. Yeah, I'm still in recovery. Coughing is very painful, but anyway, what we can do if we got ill, need to recover. So, okay, recap ya. Okay, maybe around 5, maybe before we just stop. Maybe around 5 something we stop. So no need too long. I also give you more time. So the last week we discussed about greedy algorithm. Yeah, that we need to be very wise. That seems like everything can be solved. I mean, complicated problem by DP and program, but sometimes it is overkill. So be careful. Yeah, but if, for instance, we want to gather some grass in our backyard, so we don't need to use excavator. Maybe only use at most maybe that scoop, yeah, or that pacul, yeah, that plow. But or maybe even our hand is enough. Yeah, no need excavator. So it doesn't mean DP can be a remedy, panacea for everything. No, so let me be careful about this. Grid algorithm, yes, the risk that we can stuck in local optima, but if we can use wisely, then we can get this solution, yeah, in more efficient and simpler, yeah, comparing to the DP. Okay, and also we have the step, yeah, that is similar with DP, that we think that if a problem have optimal substructure, yeah, also recursive solution, and so on. So it's similar with DP. Only the thing is 4 and 5, yeah, make it maybe a bit different than DP. Then we can say this, yeah. If it is always safe to make a greedy choice, yeah, or because 3 and 4 can be exchanged, yeah, or that if make the greedy choice, then only one subproblem remains, or it's always safe. So which one you got this, and it means it's better to use that greedy strategy because it will keep you more simpler. Too much thinking and too much uh, process, yeah, in like in DP. Okay, yeah, that's in greedy algorithm. Okay, so and sometimes it work. Yeah, I mean, in many cases actually greedy algorithm work because, well, human being also greedy. Yeah, that's why this kind of approach actually is very human nature. Yeah, very human nature, to solve some problem by that greedy approach. Yeah. Okay. Here we continue our lecture to graph. Yeah. So inshallah we'll discuss about the principle of graph, and then adjacency list and matrix can be used for representing that graph. Also, we discuss about 3 kind of traversing graph: BFS, breadth first search; DFS, depth first search; and topological sort. Okay, definition first. So a graph G can be defined by symbol V and E. Set of V and E is composed of V, set of vertices. V, take from this V. And then also edges, V for vertices, set of vertices V. And then E, edges, yeah, E subset of V times V. It is set of edges connecting the vertices. And HE equal to UV is a pair of vertices. So I just put starting from U, yeah, and then end up in V, pair of vertices. Okay. Then can be also UV is order. Yeah, I mean order means you have, say, direction, question this, UV. So if G is a directed graph, have a direction. Okay. For example, I have vertices A, B, C, D, E. So I have five vertices. So edges in here can be seen, yeah, AB. So this is our first edge, and then AC, this second edge, then AD, this, then BE, this edge, then CD, this edge, and then CE, this edge, and DC, DE. Okay, yeah. So 5 vertices, and in this case we have how many? This is 3, 4, 5, 6, 7. Yeah, 1, 2, 3, 4, 5. Yeah, 7. 7 edge. Yeah, 7 edge. 7 edges. So, so some dot. Okay. 7 edges. Yeah, 7 edges and 5 vertices. Okay. What you think the application can be used for that graph? For instance, in electronic circuit. So here, let's say, what is this? It is capacitor or something, or IC. Let's say this IC. So find the path with the least resistance to ADA01. Also network, roads, also flights, communication, etc. You guys also have so-called that flight radar, flight radar 24 that can check everybody. Because it's very funny that even is a boy, quite young, and that track that Elon Musk, I think, yeah, is flight radar or yeah, and then uh, yeah, this, yeah, there's a teenager, yeah, I mean, it's how to say, for me, like the idea of that guy, yeah, a 90-year-old with a flight tracking Twitter bot. Can you take this down? It is security risk. Jack Sweeney, yeah, over Twitter DM last fall. Elon chat. Mhm. Mhm. Yes, I can, but it will cost you a Model 3 only joking unless I want to ask. Uh-huh. Yeah, because yeah, 3,000 followers is also quite, what to say, like quite, yeah, quite significant. Yeah, the thing is the idea. I like the idea. The idea that somebody can make some interesting. Yeah. It doesn't matter then you got money or not. Yeah, it's okay, like different story. But the thing is, if you can think out of the box, that you um yeah, give some different thing, yeah, interesting different thing that what can offer you. I mean, it's really good. Yeah, I think that guy of course will cut some money from Elon Musk. Yeah, maybe not necessary. Mhm. um Tesla Model 3. Yeah, but anyway, yeah, it's good. Can check, that. I like this kind of idea. Like young people should be like that. Like you guys, you really have uh uh that guy. Yeah. Mhm. Yeah, yeah. I mean, really, it's nice. Good. Yeah. Okay. Okay. What kind of terminology? So many terms in graph. So what it called adjacent vertices. Adjacent vertices connected by an edge. So adjacent connected by an edge. Then three, like vertex 3 to 2, we have edges. This I mean adjacent vertices. 3 to, oh, let's say this is A. This is A to B. Let's say this is C. So A to C have one edge at least, yeah, connected by an edge, or we call adjacent vertices. Yeah. A to C, A to B, B to E, C to A. This adjacent vertices. What is degree? So degree in graph mean actually degree of a vertex. This number of adjacent vertices. Number of adjacent vertices, degree of a vertex. And then if sigma, degree of V element all of the vertices, then yeah, mean twice then the number of edges then. Okay. So how many edges this? Yeah, I have 1, 2, 3, 4, 5, yeah, 6, 7. Yeah. Right? Is correct? Yes, yes. So 4, so 7 mean the sigma degree of every degree of every text mean 14 twice, right? 2 times 7, yeah, times 7. Since adjacent vertices each on the adjoining edge, it will be counted twice then, yeah. Okay. Yeah. Then degree of A, yeah, should be 2, yeah. Like A to B, A to C, yeah. So have 2. That's why, like, if you have 7 edges, it means you have the sigma of degree of a vertex and total even 14. And then path. What is path? Path. Sequence of vertices V1, V2 until Vk such that consecutive vertices Vi and Vi plus 1 are adjacent. Path. So for instance, if I have A and then go to B, then I say go to C. If it is, I put make it easy direction, yeah. So it means path. So I have path A to C then, yeah. Okay. Such as consecutive and vertices Vi and Vi plus 1 are adjacent. I say this is Vi here and Vi plus 1, yeah, in C. Vi plus 1. So it means adjacent, yeah, adjacent. Simple path. What is simple path? If you don't have any repeated vertices, no repeated vertices, your simple path. Okay. A, B, yeah, A, B, B, and then E, D, C. A, B, E, D, C. Okay. Then back to E then, yeah. This will be back to E. Okay. So this will be E here. And then B, E, D, C. Okay, correct. B, E, C, B, E, C. Correct. So no repeated vertices. So cannot this, yeah. I mean, E no, because you repeated vertices this, so it's no. So no. So only this A, B, E, D, C, yeah, not back to E, because see, no repeated vertices. Okay. If E, actually I already have this, yeah, E, this, so cannot. This nothing, nothing repeated. This also nothing. Okay. Once again, A, B, D, C, okay, but not E. Yeah. Then cycle. What is cycle? Simple path is the same like this. Simple path, except that the last vertex is the same as the first vertex. Last one, the same like the first one. For instance, I start from A, then go to C, and then go to D, and then back to E. Yeah, you have cycle like this. Yeah, cycle. Or like this. Cycle. ACDA. ACDA. See that first one, the same like the last one. Because the last one back to the first one. Oh, like bicycle, yes. Bicycle. And what is the connected graph? If you have a graph where any two vertices are connected by some path, call it connected graph. Connected. If any two vertices are connected by some path. So here, so if you have A, then B, C, D, E, you can check, yeah. Any two vertices in that graph always connected by at least one edges. One edge, it means some path, at least one. can be more. Yeah. A to B go A to E to B also can so on. This is not connected because let's say this is A, this is B, this is C, D, E. Nothing from D to this A. Yeah. Nothing from A to D, for instance. Yeah. Nothing from B to D and so on. Yeah. So it is not connected. I mean, you can have like boundary like this. Yeah. Okay. Then subgraph, subset of vertices and edges forming a graph. So you have subset of vertices and edges, which can form any graph. Subgraph. And then connected component. Connected component. This maximal connected subgraph. For instance, the graph below has 3 connected components. So graph only one node here. This, or let's say one node this. Then only this. What to say? One node, no, 2 nodes and 1 edge. I mean, this one part. Yeah, this. So share this. Okay. So there this. So share this. Okay, this 3 connected component. Tree, or somebody also call it free tree. This connected graph without cycle. Without cycle. So there is nothing from the last one back to the first one. Without cycle. Tree. Then forest, collection of trees. Collection of trees. It's forest, yeah. That's very funny actually for me that that in Chinese character I like this, yeah, that if only one, yeah, this we call it mu, yeah, mu. So like one tree. And then if two, we call it lin. It is also forest actually. And then if it is three, it is already forest actually. This, yeah, the character, maybe big forest, yeah. This is this, like three how to say, like three trees, yeah. This is already forest. For me, very interesting for the Chinese character. Get translate, girl, then detect. You said the Chinese, yeah. Oh, actually also can be used English. And then this say tree, jungle. See, lean, yeah. And then was that forest, yeah. This sun lean, yeah, this. Yeah. Actually, when tree itself, yeah, this can be mu, yeah, mu is only one, yeah. Then you can see, guys, yeah, very funny, yeah, very funny, but very interesting, yeah. Mu, because it's second tone, the last tone, yeah, the fourth tone, mu. Then we check that forest. This, this is be English to Chinese traditional. Yeah, I have just copy it, yeah. This, okay. This actually already forest. This, yeah. Lean, yeah. And then sun. Yeah. Interesting, yeah. Very interesting. Okay. That's why I like to learn about language, because when I was in Taiwan back to time, really so interesting to learn Chinese culture through the language, the Donghua or Mandarin Chinese. Okay, how can we represent a graph? To start with, we can store the vertices. So because I mean on the vertices and edges, into two containers. It is to facilitate how to save, how to represent the graph, and we store with each object reference to its start and end vertices. So start and end, vertices, like this, yeah. For that, that is flight. I think flight graph, in America. Yeah. So you have TW45, UA United Airlines 120, America Airlines 49, and so on. Yeah. Go to San Francisco, go to like Los Angeles, and so on. This. So this is the how to say to starting with, yeah, starting with is easier. Then we have so-called edge list, and that's easy to implement, very easy to implement. Finding the edges incident on a given vertex is inefficient anyway, since it requires examining the entire edge sequence. And so you put, yeah, this is Boston, for instance, yeah, Los Angeles, JFK, it's like that, Miami or something in San Francisco. It's inefficient because, yeah, you need to require examining the entire edge sequence. If you want to find, yeah, some of them. Okay. So how many edges? A lot of edges. Edge list. So it was only this store, and then yeah, yeah. Starting and ending point, yeah, need to head up. And then also another idea, oh, it is too complicated, like inefficient. What about so-called adjacency list? Adjacency list. The adjacency list of vertex B is a sequence of vertices adjacent to B. Represent the graph by the adjacency list of all its vertices. For instance, A. I start from A. So A and then go to B. So here, yeah. Then also A go to C. Correct. Also go to D. Then let's say V, B. B go to A. B go to E. This. You also get this. And so on. Okay, so it's called adjacency list. It's quite okay now, yeah. So space use then was the big data and then how many what's that? How many vertices? No. How many and so can be let's see after that, yeah. Okay. So it can be big data n plus sigma degree of vertices. Your vertices V. Big data n plus m. Data n plus m. Can be this, yeah. How many vertices and how many edges. So it is correct, right? Yeah. N plus m. How many vertices? How many edges? Okay. So about vertices, let's say m. How many? And then for edges, n. The space is quite okay, yeah, for the space efficiency. Okay. And the other one, representation way is not just adjacency list, but also so-called adjacency metric. So metric M with entries for all pairs of vertices. So I have metric M with entries for all pairs of vertices. So Mij true means there is an Hij in the graph. Is true. If false, there is no Hij in the graph. Then space is like how many vertices. So n is only, this is when vertices A, B, C, D, E. So big O, and square. Yeah, and square. But I'm saying this, it is false because of course this false, yeah. You don't have H to yourself, right? But A to B have true. Okay. AC true. Yeah. This AB, AC, AD true. AE no, false. That's why this is also false. Correct. Okay, so meant big O and square, where n equal to what? The number of vertices, and yeah, vertices. Okay, and then continue for graph searching algorithm. Systematic search of every edge and vertex of the graph. Because we are not just random search, but systematic search. And then we have graph G equal to this set of vertices and edges is either can be directed or undirected. I mean you have that arc. Yeah, this is no if undirected. Today's algorithm assume an adjacency list representation. Because this is also okay, easy. This similar, yeah. This is what's that? The number big O and square. I mean number of vertices. This is number of edges plus vertices, similar. To this algorithm, I just list an application, for example, for compilers. Anyway, we want to find if then else blah 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 compilers really graphics, especially now so many graphic, very sophisticated game mesh solving. I remember at the time when I undergrad also our assignment is to have mesh like red on mesh or red in mesh. And also for mapping, especially for Google Maps, I mean the application like Gojek, many things. It was we are not so into that map, and then when the Google Map also was that that game, that game. So Gojek, mention Gojek, go Grab. Also, of course, they need to find, let's say, the shortest path. If they have maybe some difficulties, let's say a traffic jam, or maybe some accident, so they need to updating. And also, let's say when a Gojek driver or Grab driver need to pick you up in some particular thing, and they need to have this, so like Grab searching, of course, should be the shortest path, in the sense of time, maybe. Remember, it's not about maybe shorter, but you because of traffic jam, so maybe you can detour a bit, but it is make it faster. And then for networks, it can be for routing, searching, and pastoring, etc. Okay, the first one, BFS, breadth first search. BFS, maybe you guys already know, traverse a connected component of a graph. So this connected, otherwise cannot connect it. And in doing so, define a spanning tree with several useful properties. Whereas in an undirected graph, G is like wandering in a labyrinth with a string, undirected. So you don't have arc, you don't have this, but connected. It's like a wandering in a labyrinth with a string. The starting vertex S starting. It is assigned a distance 0. Of course, it is from yourself 0. So we have S, breadth first search. So it means you need to spread out, not to deep first. You cannot dive deeper, but make it spread out as wide as possible. Breadth, like breadth, wider, In the first round, the string is unrolled. You like have a string or like a rope, You put in the some particular place, the beginning. Then you put it there, and then you roll. String is unrolled. The length of 1 inch is the first round. And all of the edges that are only 1 inch away from the anchor are visited or discovered. And assign distance of 1. So like say if I have S this, then I go to here, like say this is A, let's say this is B. So here, and then this is a 0, and then I unroll this because only 1 edge, just 1 edge. And then you discover A and B then, and so on. And assign distances of 1. In the second round, all the new edges that can be reached by unrolling the string 2 edges are visited and assigned a distance of 2. Okay, but like this is E, this is F. So go here. This also, I only have 1. Let's say this is D. So 1, 2, 1, 2. This. Okay. And assign a distance of 2. This continues until every vertex has been assigned a level. The level of any vertex V correspond to the length of the shortest path in terms of edges from S to B. Term of edges from S to B. This is the algorithm. Of course, it's easy, not that difficult to understand. BFS, graph G, starting point S. For each vertex U, element V, G minus S. And set, of course, S itself, yeah, no need to count. And then you assign white, white color actually, white color type, white color to color index U. Then for distance, then you assign infinite, yeah, du. And then for this pi, yeah, pi, you pronounce pi, yeah. For predecessor, yeah, predecessor of U, the vertex before U, of course, nil, nothing, nil, predecessor. Okay, this is for initialization, yeah, instantiation or initialization. Okay, and then finish. And then for initialization for BFS with S. So you need BFS with S. No, color of that index S you set gray. And then distance of S, of course, 0. Yeah. And then predecessor of U, of course, still nil. And then Q, you put the set, yeah, S for Q. So we start from S then, right? Okay, and then we handle all use children before handling any children of children. Because it is BFS breadth, so make it wider as possible, not dive deeper. And so you have Q, yeah, okay, I have Q, while Q is not empty, it's not empty. Then do. So head of Q, you send to U. Then for each V element of adjacent U, do. Okay, and then white, if color V equal to white, remember this white, yeah, this initial segment. Then okay, you make that V, yeah, the color of V become gray, color index V. And then of course distance need to be increased by 1, yeah. Remember it is undirected, so there is no arc, yeah. So it is like 1, let's say this consider only 1, like also like 1 distance, yeah, one distance unit. Okay, so the distance U plus 1. And then now of course, yeah, you can see the predecessor, the vertex before U. So U put as predecessor of this, yeah, predecessor U. In the, how to say that, something like this S, and then put this one like this. Let's say this is A, yeah, and then this B. So predecessor of A, of course, S. Yeah, predecessor of B, of course, A. So, okay, and then in Q, V. So that V and Q. When you put V and in our Q, yeah. Remember NQ and DQ. Yeah. So now V become part of our Q. That's why I put in Q. V in Q, Q, comma V. If it is finished, then DQ, Q. Like just kick out after finish. And then after finish, you need to send the color black to color index U. Okay. That's the example. Don't worry, it's not typical at all. So I have this RSTU VWXY. Okay. And then it was all infinite, yeah, this infinite. Okay. So Q, of course, the number 1 S and distance 0. Yeah. And then in the beginning become gray, yeah. Where is this gray? It's gray. Gray. And then 0. Yeah. S from S and distance 0, because it's by himself or herself, because there is no distance for yourself. Okay. And then you need to check which one after this. Oh, I have actually 2, yeah. So the adjacent of S, of course this, yeah, W and R, right? Which one first? Let's say W first. This one W, then go to that Q. This is V, yeah. Go to Q this, right? And then 1 the distance, right? Likewise, the another adjacent is R. Yeah, R. This. So go to Q. And so here. So Q now have W and R. Let's say from left, yeah, left first. So W first and then R after W. Okay. When it is already in R and W, of course, become black. It's become black. It means already finished this. They finish this. Okay. So the edges also finished. Yeah? They are black and black. And then the infinite, it was 0. Yeah. The distance we assign 1. Then here 1 and also 1. So the same like this. Okay. Then from here, you have to find, remember, this as wider as possible, right? So now after this is black, yeah, it means what? After black, yeah, I mean this blacken mean W finish, W finish, W finish. I mean we assume that W is we proceed first, and then we only have R, then yeah R. So we have R this. Then you can check R, yeah, R. So R you have what? You have I mean after W finish, yeah, after you W finish, okay. But in W finish, in W finish, yeah, this, yeah, so here. So before you have to pull, yeah, when you want to kick W, but before, what is the adjacent of W? Oh, you have T and then X. That is why T going to our Q, yeah, and then followed by X, and this followed by X. Okay. Yeah. Then you can kick W, yeah, finish. Okay. And then blacken. Yeah. So this is finish, and then okay. So actually W finish. When W finish, so we push that W. Yeah. Likewise, like when S finish, yeah, S finish this, see, S finish, yeah. Then we cross the S, yeah. Okay. Okay, so RTX, RTX. So what we need to proceed first? Of course, R, yeah, R. Then R. What do you have after R? You cannot get to S because it's already black, yeah, blacken. It means already finished. So you only have that V, that is. Okay, okay, and then V, you go put it in that Q then. Oh yeah, before the distance, yeah, when you T and X, so this distance is 2 and 2. Likewise for R is the same. This also 2, this, yeah. Okay. So we have TXV, yeah, with distance now 2, 2, 2. Okay, yeah. Then of course we will kick R, yeah, after that, yeah, R. Because R already also blacken this. So it was S blacken and then W blacken and then no R. If you kick that R, then you have TX and then V. Okay, now proceed with T. This. Okay. Easy. Yeah, okay, yeah. So actually wanna kick T, yeah. So what is T? Oh, actually I only have, well, can be have back to W, but cannot because blacken, yeah. And then you have X. You have X. Yeah, yeah. Sorry, you be here, yeah. Okay. Like this, yeah. So after got the XV, yeah. So no T. No T. Yeah. This. Yeah. Wanna proceed T. So what you have T. Okay. So you have U, yeah, and also X, right? You have U and also X. Okay, but remember X already have there. I already have there. Okay, so you will go to then U. It's like U will go in here. Oh yeah, this X already in here, yeah, X. That's why you don't need to put against this X. Because already in this Q. So now you push U, go to our Q, U. And then the distance now is 3. Yeah, 3. Okay. Okay, we know to proceed. Okay, after T finish, yeah. Then you kick T from our Q. Now we proceed what? X, yeah, this X. So after X, what do you have? Of course, only Y. Yeah, because you cannot go to T, the blacken, cannot go to W, blacken, so only Y. Okay, then Y go to that our Q. Okay, and then the distance 3. After finish, or the blacken, yeah, then kick the X, yeah, this. Now we proceed V. V. The V in here, yeah, V. You have nothing, you cannot go to R, yeah, because R already blackened, right? Already blackened. That's V. Like this. Can be yes, okay, yeah. V, yeah. V. Then you have yourself, you don't have anything can be visited because that R already black, yeah. It is blackened. So mean you just can cross out V. Yeah. Okay. V, okay, this blackened. Then you after cross out V, then you have U and Y. Okay, you now proceed. Yeah, U. Yeah, U. This, yeah. Have actually Y, but already you already put it, yeah, in your Q. Y. Okay, here already. So finish then, yeah, because we cannot get another one. Okay, blacken. We need to cross out this. Now you only have Y. Yeah, Y. Okay. And Y also cannot go to U, yeah, because this is blackened only in cell. Then finish then. Okay. Let's cross that Y. Then this is blackened. Okay, finish. Q become empty. Yeah. Red. That's why we know back a bit in short to good, yeah. This, yeah. This while Q not empty, yeah. Otherwise will go forever, yeah. Okay. Okay. If we notice, yeah, what BFS, of course, we notice because this graph only deal with V, yeah, vertices and edges. Graph G equal to VE. Vertices are NQ'd if the color is white. Yeah, NQ'd. Go to that Q. If it is white. Assuming that N and DQing, like NQ, like NQ and DQing task, DQing takes, yeah, big O one time, I mean constant. You only put or push that push and pop, yeah, push and pop, let's say, yeah. NQ and DQ, push and pop, yeah. Because it should be only big O one time, I mean constant. It is constant, 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 yeah. The total cost of this operation is big OV, yeah. Remember, it's only how many vertices? How many vertices? Yeah. Remember what we Q and DQ is that vertices, yeah. This is vertices. This is vertices in our Q. That's why total cost and queuing and DQing is big O V. And then it is adjacency list of vertex is scanned when the vertex is DQ'd and DQ'd, yeah. And only then. The sum of the length of all lists is big data E, yeah, of edges, yeah. Okay, sum of the length of all lists. Consequently, yeah, yeah. Big O E time is spent on scanning them. Big O time spent on scanning them. Okay, for initialization, the algorithm takes big O V. Yeah, you have to scan all. Yeah, of course, this is would be big O V and this initialization. This, yeah, initialization. Okay. So total running time is this, yeah, big O V plus E, linear in the size of the adjacency list representation of G. Total running time. This, yeah, big O V, big O V plus E. Okay. Okay, now we try to dive into the so-called BFS properties. Given a graph G equal to set of V and E, BFS, this covers all vertices reachable from a source vertex S. So S, then want to go to anything reachable. It computes the shortest distance to all reachable vertices. It computes a breadth first tree that contains all such reachable vertices. For any vertex V reachable from S, the path in the breadth first tree from S to B correspond to a shortest path in G. So you have a S and anything with this. Of course, this is like in between, yeah, maybe T, maybe X, or V, whatever, yeah. So if for any vertex V reachable from S, so anything, this is go to the V reachable from S, then the path in the breadth first tree from S to V correspond to shortest path in G. So this is be the shortest path. Okay, now talk about BF3. BF3 breadth first tree is about 3. So pi, predecessor, yeah, this pi. This for predecessor. Predecessor subgraph of G. G pi equal to P pi E pi. P pi predecessor of V, yeah, is equal to V element V, like vertices element set of vertices where pi index V not equal to nil. Union that S. S and go. S should be of course the first one, yeah, before going somewhere here, U, V or whatever, yeah. Likewise, E pi equal to pi index V, comma V element set of edges, V element V pi minus S. Okay, G pi is a breadth first tree. V pi consists of the vertices reachable from S. This go to V. And many, this is many vertices reachable from S. And for all V element V pi, there is a unique simple path from S to V in G pi. That is also the shortest path from S to V in G. Correct, yeah? Unique simple path from S to V. The edges in G pi are called the three edges. The edges in G pi are called the three edges. Okay, so now DFS to make it comparison. Yeah? Comparison. DFS is undirected also. In this case, as undirected, there is no arc. No arc this. Graph G is like wandering in labyrinth with a string. It's like a BFS, yeah. It's only wandering in a labyrinth. A labyrinth with the string is BFS. BFS. Just you spread out, make it wider. But now you also have this and a can of paint. So this DFS, yeah, like a BFS with a string, but we have another weapon, another tool, another helper, a can of paint. Okay. We start at vertex S, tying the end of our string to the point. So we have in S, yeah. Then your string, you go here. This A, B, C. Yeah, tying the end of our string to a point and painting this S visited or discover. Okay. So you go ABC and then you paint this S. Painting S visited discover because okay, done. Then next we label S as our current vertex called U. Because then S. Then after S finish you call it U. Because we will go to V. Like UV. S first, yeah. And then after finish you label U. Now we travel along an arbitrary edge UV. UV. If edge UV leads us to an already visited vertex V, so already, we return to U, and then you go to here, yeah, go like this at to T, yeah, go this, and then actually, you go to let's say what, so you know you are now here, yeah, you are in here, this T, and actually T also go to let's say C, yeah, because it already label, yeah, so you back to B then. You back to U and then V. V want to go, let's say this is C, but this already visited. So you back to U. This. So we return to U. This. If vertex V is unvisited, unvisited. UV, U and then V. Unvisited, we unroll. We unroll our string, move to V, and then pen V visited this. Set V as our current vertex means become U, new U, new U, and repeat the previous step. It's already done, yeah. V also done, become this new. So you have string and also can of pen. Eventually, we will get to a point where all incident edges on U lead to visited vertices. Already been visited. Okay, what to do then? We then backtrack. Yeah, we return back. Backtrack by unrolling our string to a previously visited vertex U, V, visited vertex V. Then V becomes our current vertex and we repeat the previous step. Then U and then become V and then we go actually all visited. Then you have to backtrack this. Yeah. Then V become our current vertex. I mean this become like kind of U and kind of like new V and so on. Then if all incident edges on V leads to visited vertices, we backtrack as we did before. We continue to backtrack along the path we have traveled. So the one that you already been visited. Continue to backtrack along the path we have traveled. Finding and exploring, finding and exploring unexplored edges. Because maybe I say in some part this is already visited, but actually in here no. Okay, then you can explore this. Then okay, you can backtrack after all visited. Finding, exploring unexplored edges, and repeating the procedure. This is the algorithm. DFS G for graph G. Then for each vertex U, element V, G, for this is V, do color U. So white, you assign all of the color index U from white. You need all vertices. And 0 for the time. Okay, then for each vertex U element VG, do if color U white, then DFS minus visit U. Because we're preparing for U to V. DFS minus visit U. What is DFS visit U? Oh, sorry. Then DFS visit U. This is like this is not minus. This is the name. I mean here. And you call this DFS visit U. Okay. Number one, you assign gray. So white vertex U discover U, then V. I mean the first one. Then U and then V. So white vertex you discover. I mean, okay, you already just started and then you step over in U. I mean, white vertex you discover. I mean, you need to assign the gray color to color index U. It was white, yeah, become gray now. Then also mark with discovery time. Discovery time. So this time, I mean, discovery time when you find it. When you find it, you found this discovery time. Time put in the index U. Okay. So it means what? Discovery, yeah, discovery time, discovery time, and then the global time. Well, that means time plus one. So this is global time. Okay, then need to visit children recursively. That's why we put then the FS visit, and then this is because it is recursive. Okay. Explore all edges UV. For each V element adjacent U. Remember, we want to U and then want to go to V. So for each V element adjacent U, do if color V equal to white. If color V equal to white, when still not yet visited, and then you step over there, and then DFS visit again. I mean, actually this is recursive. Okay. I mean, and then all white, yeah. And then if not this, blacken U if it is finished. Blacken U, if it is finished, mean you go to V and then all finish. Then blacken, I mean you already explore all from U. Need to blacken U. Black need to assign to color index U. But it blacken. Then mark with finishing time. So F here, finishing time, FU. Time assigned to F index U, finishing time. And again, take global time plus 1. Okay, initialize ya color that color ya color is not color ya color all vertices white. Initialization ya all white, all colors are white. And then when visit each and what is that? Visit each and every white vertex using DFS visit. This is the name of that procedure, recursive procedure. Visit each and every white vertex using DFS visit. And then each call to DFS visit U, routes a new tree of the diverse forest at vertex U. When you U and then go to V, so actually you have new route, yeah, new tree of the diverse forest at vertex U. You like dive deeper, yeah, go deeper there. The root is U, yeah. Root a new tree of the diverse forest at vertex U. And then a vertex is white if it is undiscovered, never been visited, white. Then a vertex is gray if it has been discovered, already discovered, but not all of its edges have been discovered. So when I have V here, so it is actually gray because okay, I visited, let's say this is a P, I visited Q, but I not visited, let's say W. So this is okay, but this is not yet. So this is gray. Yeah. So not all of its edges have been discovered. That's why it is gray. Then vertex is black after all of its adjacent vertices have been discovered. The adjacent list was examined completely. It's become black if all of the adjacent vertices already been visited. When DFS returns, every vertex U assigned. Every vertex U is assigned what? D, discovery time, DU. When DFS return, yeah. And finishing time, FU. FU. It's only FU, yeah, not F and star, no, yeah, FU. And then, okay, what about running time? Okay. Running time. Okay. The loop in DFS, loops, takes time, big data V each, because we need to count how many vertices, like big data V each, excluding the time to execute DFS visit. So it is not counted, guys. The time to execute DFS visit. Then DFS visit is called once for every vertex. Every vertex called once. It is only invoked on white vertices. And paints the vertex gray immediately. It's like, oh, S visited, U visited, and so on. Invoke on white vertices and paints the vertex gray immediately. For each DFS visit, a loop iterate over all adjacent V. Like say O, U, and then V, and then all this adjacent V. And the adjacent V here. The total cost for DFS visit is big data E. Yeah. And we check if sigma, yeah, V element V, adjacent V, equal to big data E. And this. And this why like this big data E plus this. Yeah. So this why the rank time of DFS is big data V plus E. Actually the same like BFS, yeah. Big data V plus E. You can check again for BFS. There is BFS, guys. This, yeah, this big OVE. So it's equal. Big OVE equal. Example, yeah, don't worry. So I have U, V, W, X, Y, Z. Yeah, you know, it's of course different because you have backtrack. Yeah. So let's say I start from I'm still recovering, not yet recover full. Yeah. Nice. Okay, you yeah. So I start from index 1 and slash means slash because it's not yet finished. If finished, okay, I will put all. Yeah. So this and then it was all white, yeah, but because we already start by start from you and then gray, 1 over something, yeah, still not yet. Okay, and then which one? Because this there is an arc. Yeah. Then I go. It is not like PFS that okay, U adjacent is U and yeah, it's usually V and X, yeah, and I take what of them? No, yeah, it is DFS only one, and then assume I take P. This why, and then I have 2 in here. This over that. It is discovery, yeah, and then finish. Discovery time and then finish time. DF. So this for the first one. This for discovery. Finish not yet. Yeah, this one all not finished. Okay, yeah. And then see that the arc this blacken actually already. I mean already visit, but we don't put that finishing time yet. Yeah. Okay, after 2 V, what do you want to go? V. Oh, actually I want to go to Y. Okay, and then put that discovery time 3. Yeah. This is a blacken for that arc. Okay, Y. What do you want to go? Oh, actually I want to go to X because the only one. Yeah. Okay. X then 4. Okay. Then actually after X, I want to go back to V. This yeah, B. So like, but it is already gray. Yeah, already gray, right? This is already gray. Remember, this cannot go to U. This is the arc in here. It's only go to V. Yeah, this already blackened, but it's already gray. Yeah, it already gray. It means okay. Actually, already visited. It means that X is already. I mean, all of the X vertices, adjacent vertices already been discovered. This is why we blacken. So it means we have the finishing time first. This 5. Yeah, and then this vertices, this vertex X become blackened. Okay, finish. Yeah, sure, finish. Your job finish, right? Okay. Then continue. Then backtrack, right? Backtrack. So after X, backtrack with Y, what? Y, yeah, Y, Y. Then Y also cannot go anywhere, yeah. So that finish. That's 6. Okay. Then after that, backtrack, yeah. After Y, before Y, what? V, yeah, V. V. V also cannot go anywhere, yeah, because then finish 7 and blacken, yeah. It was blacken the Y. Then V also blacken that vertex. Okay. Okay. Then after that, backtrack, yeah, backtrack after U, after V, of course U, yeah, this go here, backtrack. Then it is 8, okay, 8. Then blacken the U, right? Okay, finish this part, yeah. Then we have to go, even though this act this, yeah. And then you need to start with any starting point, okay. And then we assume W, okay, no 9. And then it is white and then become gray when you step over, and the discovery time is 9 now. Okay, and then where you want to go? Actually you can go to Y. I see this. So this is B. I mean F. Actually there's there is yeah. I forgot to say. So B for backtrack or backward, yeah, backward. I mean like go back, yeah, backward. F for forward. See, actually U when you go when go V, yeah, go to U, backtrack. Actually, yeah, you can go to X, right? But remember, X already what? Blackened, already blackened. That's why this forward, well, cannot go because it is blackened. If it is gray, yeah, it is kind of backtrack, like B. Yeah, but this go forward, yeah. It was backward, but this actually forward because that X is after U, yeah, discovery time, yeah, especially of course finishing time, yeah. Sorry for discovery time, yeah. And that's why this F cannot, that's why it become blackened. Yeah, sorry, that for F need to give explanation. Yeah. Yeah. Okay, so back to yeah. So 9, yeah. W 9. Actually, I can go to Y, yeah, because I have an arc here. But because this is already blackened, so this is C, cross, cross. You jump to the one, like crossroad, cross. And it is blackened, you cannot go there because already blackened. Okay, the only one I got to Z. And then case discovery time 10, right? Okay, and then after Z, actually you have arc to yourself, but it is already gray. Yeah, it is already gray. This is like like back, uh, back, back arc, or back. Yeah, because it can be backtrack. Forward path, or forward arc, or backward arc, or backward path. It's already gray. It means you already visited. Okay, and then become blackened. 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 Yeah. And then okay, of course, backtrack to W. Yeah, W. Go back here. And W can go anywhere. Yeah. So okay, finish the finishing time. Yeah, 12. Okay. Okay, and then we discuss what's called predecessor subgraph. Defined slightly different from PFS. Different. PD. Predecessor. Yeah, PD. Predecessor. G pi equal to V. Then only this is there is no V pi, but only E pi. Then E pi equal to pi, predecessor of V, comma V, element edges, V element V, vertices, and pi V not equal to nil. The predecessor subgraph of a depth first search, because we actually still talk about DFS. That's why it's not the same like DFS. Same. Yeah. The PD subgraph of the depth first search, predecessor subgraph, form so-called DF forest, depth first forest, composed of several depth first trees. The edges in GPy are called tree edges. The edges in GPy are called tree edges. Okay. Another one we call it, which is called time stamping. The DFS algorithm maintains a monotonically increasing global clock. Yeah, always go up, at least the same or go up. Yeah, this monotonically. Never this go down and yeah, never. Always the same or up. Monotonically increase. Discovery time du and finishing time fu always monotonically increase. Du and fu. For every vertex u, the inequality du always less than. I mean du discovery time always earlier than finishing time. Du less than fu must hold. You can check here. Yeah, always and always. That the first one always earlier than the second one. You can check. Yeah, always. Discovery time D always earlier, always less than finishing time F. Correct, yeah? Okay, for time stamping, see, vertex U is white, yeah, before time du, correct? Of course, yeah, in the initialization, before time du, before discovery time come up, always white. And then gray, the color become gray between time du and time fu. Because maybe, yeah, like this U and then V, maybe they still have edges that we have been discovered. That's why still gray and black thereafter. I mean after we totally visited all, I mean become blackened. Notice the structure throughout the algorithm. Gray vertices form a linear chain. Gray vertices form a linear chain. Okay. Then correspond to a stack of vertices. Stack of vertices. Stack. So yeah, go here. This is A, and then B, then C. I mean, A will go later on. Yeah, C first. What's the stack? Stack of vertices that have not been exhaustively explored. Have not been exhaustively explored. Because DFS visit, our procedure started, but not yet finished. Not yet finished. And we have so-called DFS parenthesis theorem. Discovery D and finish time F have parenthesis structure. Represent discovery of U D of U with left parenthesis this. Left parenthesis this, yeah. And then U. Represent finishing of U F with right parenthesis U this. History of discoveries and finishing makes a well-formed expression. History of discoveries and finishing makes a well-formed expression. Is well-formed expression. It means parentheses are properly nested. So you can go like this. Then you can go like this. Question 2 times 3. And it was that when it is 7. Maybe this is time, let's say 5. So this first should be, and then this. Okay. Intuition for proof. Intuition, I mean by your intuition. It's not yet proven by mathematics. Yeah. I mean, to say not yet proved by numerical thing or by any lemma or theorem. Yeah. So the intuition. Any two interval are either disjoint or enclosed. Disjoint or enclosed. Disjoint like this, yeah. Disjoint mean this and this. This disjoint, yeah, because not intersect each other, yeah. 7, I say this is 7 plus 1. I say this 2, yeah. A time I say 3. This disjoint, yeah. Or enclosed, like this case. This case enclosed. 2 times 3 is inside that. Let's say 7 times that times 3 plus times 5. Okay, so this and overlapping intervals would mean finishing ancestor before finishing descendant or starting descendant without starting ancestor. It means cannot be done, yeah, actually. Yeah, I mean cannot be happen because you would mean finishing ancestor before finishing descendant. It's impossible, right? For instance, like this, yeah. For instance, this in here overlapping interval, yeah. I mean like this. It should be like this. It means discovery D. Let's say this is 1, yeah. And then finishing should be, let's say 7. Discovery is, let's say 3, yeah. And then finishing, let's say 6. Then okay, right? 6. Okay, right? But if overlapping like this, yeah. So if like say that case again, yeah. So it should be 1 and then 7, yeah. 7, yeah. Then 3, then was that 6, yeah. 6, right? But because overlapping, yeah, it means true, right? That finishing ancestor before finishing descendant, right? Or starting descendant without starting ancestor. Become very stupid, right? Yeah. If overlapping, then become stupid because 3 7, yeah. And then this is not finished. If say this overlapping, yeah, it should be finished. This, yeah, should be finished, right? But you go here first, 6, yeah? And then become stupid, yeah, right? This we finish this, then you go here, but no, and then 7, it is later on. This is finished in here. If I can be seen finishing ancestor before finishing descendant or starting descendant without starting ancestor, become very stupid. Yeah, it's not happen. Then you can check here. Actually, this is the same like what we have. Where is our example? This, right, guys? This. Okay, see, that should be 3, 6, 2, 9, 1, 10, 11, 16, 4 over 5, 7 over 8, 12 over 13, 14 over 15. Okay, and then we can check. Yeah. So S, yeah. And then which one need to finish first? And let's see that parenthesis, yeah. So X, or you wanna check from the last one, yeah. That U. Okay, which one? Yeah. So this, yeah. So starting in this is, yeah, 1 and finish in 10. Which one? That S this. But you cannot do this, yeah, because this finish in 10, right? So you have to finish which one, the first one finish? X, right? Say why this. The parenthesis is correct, yeah, XX. Because you finish in 5. So this is the first one. And then after 5 finish, yeah, the finishing time. See the finishing time, F. Then you can see the Y. Y. Finish in 6. Right, this. The X and then Y. Finish in 6. Which one? This. The second one. This is the first one. Finishing. And then after that, W. Finish in 8. So this. This is number 3. Finish number 3. Then after that, so C also, yeah, this is, so the parenthesis correct. Yeah. Y also correct. Yeah, after this, X, and then this Y. Correct. Then double W. And then Z. Z finish in 9. Z. This. This is number 4. This is correct. This Z. Then go until this. Okay. And then after that, what? B. Yeah, finish in 13. B. This. This is number 5. C parenthesis correct. And the other, and then U. U finish in 15. This. U. This. This is number 6 then. And then later on, the last one, yeah, the T. Yeah. So T this finish in 16. Last one, this. The number 7, and yeah, this. Okay. See, yeah, the parenthesis properly. Yeah, the nested. There's overlap. Yeah. Okay. Okay. DFS age classification, like just to say, yeah, 3H gray to white, gray to white. Encounter new vertices of white. Then so-called back edge, you know, so like B, backward, back edge, gray to gray. This is gray, this is gray. Then B. From descendant to ancestor, correct, yeah, because it was from here, Y, Z, and then W and X, and then X wanna back to Z. Z is already ancestor. X is descendant. This is descendant. This is ancestor. So descendant to ancestor, correct. B, back edge. 3 gray to white is easy. I mean gray, and then the one that new vertices, because what it means you haven't been there. Then for what age? Gray to black, F, that F1. What age? Gray to black. From ancestor to descendant, this. Right? Because S is ancestor. Then go here, V and W, and then this is descendant. So ancestor to descendant. Then cross age, gray to black. Reminder between trees or subtrees. Between trees or subtrees. This C. C should be here, yeah. Yeah, this also C. Okay. I think easy to check is the land we have. This, yeah, C. Yeah, this. Yeah, easy. See, yeah. cross. Okay, it's not easy. It's not difficult. It's reminder, yeah. Reminder between trees or subtrees. Can we see, yeah, cross, cross, cross. Gray to black because it's gray to black, gray to black. Okay, tree I mean that from gray to white, yeah, gray to white, right? Three, this, yes, this, yeah, gray to white, 3H, gray to white, and back edge is gray to gray, GG, yeah, this, yeah, GG, gray to gray, are important, yeah, GW and GG are important, gray to white and gray to gray are important. Most algorithms do not distinguish between forward, F, and cross edge. This is forward and cross. But back, yes, it's very important, yeah, because you can check it from descendant to ancestor, yeah. And also, of course, also that tree, I mean, gray to white, because this you are what to say, fine. You just found the new frontier, the new vertices that not yet been visited. Then we move to DAG, directed cyclic graph, DAG. A cyclic, no cycle. This directed graph means there is a arc with no directed cycles, no directed cycle. Okay. Like this, yeah, you go here and then go here. That's okay. There's no cycle. So the termination is here. Okay. So this can check, is there any? Okay, this termination here. Termination here. Yeah, this, yeah. Okay, no cycle. There is no cycle here, yeah. This is termination. Yeah, only this. Often used to indicate precedences. Precedences. The one who, which one is the come first? Which one come first? Precedences. Which one is the to be picked first? Precedences among events. For instance, event A, yeah, event A must happen before B. So mean like this: A, because there is an arc, yeah, B. So A come before B and B come before C. So C is the one who finished first. Example will be a parallel code execution. I mean, when I was in Taiwan, and then we have to implement, yeah, the algorithm, to learn about that is computer architecture, ya, about parallel code execution, need to worry about, need to concern about this DAG. Inducing a total order can be done using so-called topological sorting. Inducing a total order. So which one? Oh, this is A, the first one, and then followed by B, and then followed by C, and so on. We call it topological sorting. So we check so-called DAG theorem. A directed graph G is a cyclic if and only if a DFS of G yields no back edges. Correct or not? Yeah. So DAG is a cyclic. I mean, a directed graph G is a cyclic. I mean, become DAG. Become DAG. This DAG. I mean, if and only if DFS you apply DFS on G, and then it turns that no back edges. Remember that B1. Where is that? Easy to see one. This, yeah. There is no B. Because of B, of course, it means a cyclic, yeah, cycle. How to prove? How to prove? Okay. Suppose there is a back edge UV. Back edge. Remember, yeah? Let's say A, and then go B, and then go C, and then go D, and then this is D to B. This is back edge because D is descendant, yeah, and B is ancestor, the parent, or let's say the grandparent. This in the case grandparent, because C is father of D, B is granddad or grandparent. Okay, suppose yeah there is a back edge UV. Back edge UV, it means D become U. Yeah, this is become U. Then that B become V. Then yeah, this because it's a back back edge. V is an ancestor of U in DFS forest, right? Correct. Yeah. V is an ancestor of U in DFS forest. Correct. Yeah. So B is ancestor of D. Correct. Thus, there is a path from V to U, V to U, so B to D in G and UV complete the cycle. Correct. Yeah. You just see this. Correct. Yeah. Suppose there is a cycle C. Cycle C. So the cycle C. Cycle C. Let V the first vertex in C to be discovered, and U is predecessor of V in C. V is the first vertex in C to be discovered. So I have, let's say like this, easy cycle. So let's say V is the first vertex in C to be discovered, and U is predecessor of V in C. So I have U in here. Predecessor, that pi. V is discovered first, but U is predecessor. Yeah, is predecessor of V. Okay, it is suppose, yeah, suppose there is cycle. Cycle. Upon discovering V, you got V. The whole cycle from V to U is white. Because when discovering V, I mean the new one of course white, yeah. So whole cycle from V to U is white. Yeah, because it is V to U, yeah. V to U is of white because the new one is white. We must visit all nodes reachable on this white path before return DFS visit V. Okay, before go here. i.e. vertex U becomes a descendant of V. Right, if it is white, and then of course need to explore all to the U. And because of this, it means U become descendant. Remember, if V to U, V to U yeah, is white, and become U becomes descendant if you find it anyway. Yeah. Thus, UV is a back edge. UV, yes, yeah. It become back edge because V become it is parent, become it is descendant. Oh, sorry, this ancestor not parent. Yeah. See, ancestor. This is descendant. Of course, then UV become back. Yeah. Remember, for descendant to ancestor, right? Become its back edge. How to do topological sort. Yeah. Sorting of DAG. A topological sort of DAG is linear ordering of all its vertices such that for any edge UV in the DAG, U appears before V in the ordering. So any UV, any edge, then U appears before V in ordering. So always and always this become this earlier. Then E. The following algorithm topologically sort DAG. Yeah. So topological sort G, you call DFS on G to complete finishing time. So we deal with finishing time. Actually, we discussed a bit about in that parenthesis this. Yeah. We care about this finishing time. Yeah. To complete finishing time FV. for each vertex V. As each vertex is finished, insert it onto the front of linked list. Okay. So which one the first one come? Yeah, this was like this, and then you go insert it in front of a linked list. We come here, the first one. Which one the first one finish? Put it on the first. Okay. And then return the linked list of vertices. The linked list comprises a total ordering. Okay, example this here. Precedent relations. An edge from X to Y means one must be done with X before one can do Y. So X to Y. It means you have to do X first before you can do Y. Intuition, like from our experience, can schedule tasks only when all of its subtasks have been scheduled, right? If you have a task and then many subtasks, of course, you need to deal with the subtask first and then before you go. Okay, I have this. Yeah, so this is discovery time, and then this is finishing time. Yeah, so 1/8, something like this. If I start from insert first and then tie, and then check it, this is so complicated. Yeah, actually, we have to put which one? We have to put one. Because when we say this, yeah, finishing time it is finished and insert into the front of the linked list. You can check this correct or not. 14. Yeah. Then finishing time 15. Yeah, so before. Then this is 16, correct? Yeah. Then 18 is correct. Yeah. Yeah, not the jacket. Yeah, jacket 4 and this is 5. Correct, yeah. For finishing time, correct. So that the how to say the last one put the first, and this 18 is the last one. Okay. And then it is nicely you can be seen if you want to, I say, want to put our clothes on, yeah, when we after, let's say in the morning you take a bath and want to go to campus, or you know, visit or make a date with your girlfriend or boyfriend, you know. So it means you need to put sock first before shoes. You need to put undershirt first before pants, otherwise become what? Superman. Yeah, the Superman. It's very stupid that underpants, yeah, after short, yeah, and then the Superman, the logo. Yeah. Okay, that is Superman, but we are not Superman. Yeah, undershot. I mean underwear. Yeah, underwear. Your swim pack is need to be put on before your pant. Yeah, otherwise become Superman. Yeah, the long pant, yeah, and then the swim pack. Yeah, this undershot. Then after pant, and then put shoes. Yeah, you can imagine if uh shoes first. Yeah, and then sock, and then long pant will become what then? Yeah, this is correct. Yeah, so sock, because it is 18. Yeah, the last one put in the beginning. It is like subtask, but should be done first. Yeah. Then undershot should be done first before pen and shoes. Then after pen, okay, belt. Yeah, correct. Yeah. And then okay, should be also shirt. I mean your shirt. Then belt, and then pen, and then belt. Then after that you got tie up. Yeah. And then last time jacket and jacket. Watch. Well, it is like independent. Yeah. It doesn't matter. Actually, you can put your watch when you are take a bath or in a toilet or whatever. I mean, what is independent? Because this is also independent in here. That's why this is independent. But for the other, because you already have precedence, this arc, and you have like discovery time and finishing time. Okay. So you have to put topological sort. Use DFS. Okay, running time, DFS, DF sort. It's like that DF uh, DFS what we discussed before, yeah, big O V plus E time number of vertices plus number of edges. When insert each of the this number of vertices, onto the this, for instance, shock first, yeah, onto the front of the linked list, mean big O 1 per insertion, easy. Thus the tolerating time is big O V plus E, like DFS, yeah. DFS, double is equal, yeah. Big O beta V plus E, okay. Okay, claim for a DAG, an HUV, this DAG, remember this DAG? Yeah, this. Yeah, directed acyclic graph. The claim is an HUV, U, and then go to V. Element E, edges, it means FU should be greater than FV. So this is D and F, this discovery time and finishing time. So FU always greater than FV. So this should be F. Let's say this is 18. This is like say the first one, like the 1. Yeah. So 18 FU to be greater than 1. Yeah. FV. Yeah. See this. When UV explore, okay, yeah. UV explore. U is gray, right? Because this your deficit, but all of the destination of U not yet been visited, all of them. Maybe some yes, not. Some no. That's why U is gray, correct, yeah, correct. U is gray. We can distinguish 3 cases. If V also gray, this is V. Then it mean back age, yeah. If it gray, it mean already visited. I mean you go back. This mean this is ancestor. This is descendant. It means back age. Face back age and then cycle. Yeah, already see that this E and then B and then C. Yeah, go here, and then back here. Cycle back. Then contradiction cannot. Right. If V is white, he become descendant of U. Okay, yeah, this white mean the new one, descendant of U. V will be finished before U. Will be finished before U. This V will come finished first, yeah, before U. Before U. U I mean later on. It means FV less than, yeah, because finished earlier, less than FU. Correct, right? Yeah, because it means FU greater than FV. Correct. And then another case, the last one, if V black, U, and then you go to V. Naturally, this V already black, mean finish. V already finished. If finish, mean what? Of course, this greater is finished. Sorry, if this finish, mean it is earlier finish. That's why FV less than FU. Once again, mean FU greater than FV. So correct. So the definition of the word satisfied in all of the cases. This assume it is gray and it is contradiction. So only this cannot, yeah, because it is version this package. Okay, guys, that's it. Yeah, as I said, around 5 something, yeah, finished. I also need to recover, and anyway, our material is finished. Yeah. Okay, thank you guys. Have a nice time. See you later. Assalamualaikum, and please prepare your breakfast nicely. Okay, thank you guys. See you later.
Thank you, Pak.
Thank you. See you guys. Thank you. Have a nice time. See you guys. See you later.